Year 13, Short Revision Video 11. So, this is a question which is about mechanics. It's about acceleration that's dependent on time, so non-constant acceleration in parts. But it's also linked to the idea of modelling and evaluating whether or not a model works for a particular physical situation. So there are a lot of interesting components to this question. Let's start off with the first piece of information. So the velocity of a car, v meters per second at time t seconds, is being modelled. Initially, the car has velocity 5 meters per second and accelerates to 11.4 meters per second in 4 seconds. So all of this is going to be important. In Model A, the acceleration is assumed to be uniform. So part 1, find an expression for the velocity of the car at time t using this model. So there would be a temptation to try and rush in and use all of the information that's been given at once. But let's think about this carefully. So we're assuming that the acceleration is initially uniform in this model. So what information can we fill in for our SUVAT or constant acceleration equations? We don't know the distance travelled. We know the starting velocity is 5 meters per second. The final velocity is 11.4 meters per second. The acceleration we don't know, but we would have a vested interest in finding it. And the time is 4 seconds. So if I remove s from this, we're looking for a constant acceleration equation that features v, u, a and t. So v equals u plus at. So 11.4 equals 5 plus 4a, and then rearrange this to work out the value of a. And this comes to 1.6 meters per second squared. So that's our constant acceleration. Now, the question actually, if we read it, says find an expression for the velocity at time t using this model. So we're going to use the same formula, v equals u plus at, but we're not looking for the velocity at a specific time, we're looking for a general formula for velocity. So v remains as v. Now u, we do want to use the initial velocity, which is 5, but we can now substitute in a value for the acceleration, which is 1.6, and of course, remember the question wanted the velocity at time t. So here is our answer, v equals 5 plus 1.6 t. Part 2, explain why this model is not appropriate in the long term. Now, there might well be many reasons for why the model is not appropriate, and you may well think of other ways of explaining why it's not appropriate, but let's look at the obvious facts here. If that's our formula for the velocity, then as time increases, the velocity is going to get larger and larger and larger. So essentially, it suggests that the car is going to accelerate indefinitely, and that's not feasible. It's not possible for a car to carry on accelerating forever. Cars are limited in that they cannot do that. So we need to get across the idea that it's not possible for the velocity to carry on increasing indefinitely. So, as is the way with models, we refine them. So Model A is refined so that the velocity remains constant once the car reaches 17.8 meters per second. Sketch a velocity time graph for the motion of the car, making clear the time at which the acceleration changes. Now, it's a sketch, not a plot, so we don't need to accurately set up a pair of axes, but we do need to label our axes clearly with any key points of information. So here's my set of axes. We want velocity on the y-axis, meters per second, 0, there. And we want time in seconds. So remember the car starts at a velocity of 5 meters per second. So what I would do very clearly is make sure 5 is marked on the y-axis. We then have a constant acceleration, which takes us up to a velocity of 17.8 meters per second. So remember, the velocity remains constant once the car reaches this particular value. So we want to make it clear we've got 17.8 meters per second. And then at that point, the velocity remains constant. So we want a horizontal line on our graph like so. Now, we don't know how long the car is travelling for, so I can't put anything on my x-axis there. But what I can do is I can put a time here, because that's the time at which the acceleration changes, and we do need to make that time clear. So remember, the acceleration is equal to 1.6 meters per second squared, and acceleration is the gradient of our velocity time graph. So the gradient of this velocity time graph would be 17.8 minus 5 divided by this measurement across here on the x-axis. So I'll just call that x for the moment, and that's equal to 1.6. If I solve this simple equation, x works out to be 8 seconds. So I must clearly mark 8 seconds on my x-axis there. We may add to the graph in a moment, but for the moment that's enough for part 3. Now, part 4, calculate the displacement of the car in the first 20 seconds according to this refined model. So let's now add to our graph 20 seconds here, because we're going to now calculate the displacement, which is the area under the graph. So for part 4, the area is equal to 2 sections. We have this section here, which is a trapezium, and then this section here, which is a rectangle. So our trapezium, we want a half of 5 plus 17.8 multiplied by the 8 between them, and then we need to add on 17.8 and multiply that by 12 for the yellow area. This then gives us a value of 304.8 meters travelled for the displacement. So we're now looking at a new model, Model B, in which the velocity of the car is given by a formula where v is dependent on t. So we're going to probably end up with an acceleration that's non-constant, that is dependent on time. So part 5, show that this model gives an appropriate value for v when t equals 4. So this is clearly a 1-mark question, a very short question, which just requires us to substitute t equals 4 into the correct part of the velocity formula. So it's obvious we've got to substitute into this part because t is between 0 and 8. So v is equal to 5 plus 0.6 multiplied by 4 squared minus 0.05 multiplied by 4 cubed, which gives us 11.4 meters per second. Now that's an appropriate value because it's the value that we were given in the question for the velocity after 4 seconds. Now let's read part 6. Explain why the value of the acceleration immediately before the velocity becomes constant is likely to mean that Model B is a better model than Model A. So it might not be obvious straight away as to what we have to do to approach this question. So let's break it down. It's talking about acceleration. So let's work out what the acceleration is. So remember, the acceleration can be found by differentiating the expression for the velocity, so dv by dt. So that's going to give us 1.2t minus 0.15 t squared. So it's then talking about the value of the acceleration immediately before the velocity becomes constant. So the velocity becomes constant essentially at 8 seconds. So 8 seconds is the kind of critical point here, the time at which we go from non-constant velocity to constant velocity. So t equals 8 seconds. Let's substitute that into the acceleration formula, and let's see what that gives us for the acceleration at that particular time. And it gives us an acceleration of 0. So essentially the car has reached its maximum speed without there being a sudden change in acceleration, which is what would have happened in model A. We've gradually got to the point where at t equals 8 seconds, the acceleration is 0, so we're at our maximum velocity, we can't go any faster, we can't accelerate any higher, and we're then going to hit constant velocity. And the last part of this question asks us to show that model B gives the same value as model A for the displacement at time 20 seconds. So if you remember, the displacement should be a value after 20 seconds of 304.8 metres. Now, there are two parts to the velocity formula that we need to use, and if you remember, if you start with displacement, you differentiate it to get the velocity. So if we're now working with velocity and going back to displacement, we need to integrate the velocity formula. So our displacement after 20 seconds is going to be the integral of 5 plus 0.6 t squared minus 0.05 t cubed with respect to time between 0 and 8 seconds. But then, of course, the car travels for 12 seconds, between 8 and 20 seconds, at a constant velocity of 17.8. Now, you can actually approach this in different ways. You can use speed, distance, time here because it's a constant velocity. So we can say that the displacement or the distance travelled will be the velocity 17.8 multiplied by the time, which is 12. You could also have done an integral of 17.8 with respect to time between 8 and 20 seconds, and that would also get us to the same answer at the end. So integrating, this is going to give us 5t plus 0.2 t cubed minus 0.0125 t to the power of 4. That's between 0 and 8, and then we have to add on the extra portion, which is 213.6 metres. Now, we only need to substitute in t equals 8 because t equals 0 will just result in a 0. So this gives us 40 plus 0.2 multiplied by 8 cubed minus 0.0125 multiplied by 8 to the power of 4 plus 213.6. And if we evaluate this using our calculator, it comes to 304.8 metres, which is the same as with model A.